Hey everyone, in this screencast today what we're going to talk about is something called Hess's law. Hess's law involves enthalpies, which is something that we've been talking about a lot, and as you can see by looking at this table to the right here, enthalpies are something in which the values for specific reactions have been recorded. So for example, when CH4, which is methane, reacts with 2 moles of oxygen gas, we create carbon dioxide and water. And if 1 mole of methane were to react, that means that we would produce 890.4 kilojoules of heat. Now, as a scientist, it's really nice to be able to have these tabulated values for us to be able to look at and see for a reaction how much we should expect to get if we're performing a reaction. Sometimes, however, there can be reactions that we either A, can't do because it's impossible to conduct those reactions, or B, we don't have the correct equipment in order to do them. So for example, if we were trying to do a combustion reaction and measure the heat, but you didn't have a bomb calorimeter, it'd be very difficult to do that effectively and correctly as well. So we use something called Hess's law instead, and this is named after a guy named Hess, and essentially what he did was he realized that he could use other reactions and look at their enthalpy data, look at how much heat they produce, to calculate what the enthalpy should be of a specific reaction. And the whole reason why he's able to do that is because of this point down here, that enthalpy is a state function. This means that only the initial and the final states matter. So essentially he can kind of manipulate the data that he's looking at so that it has the reactants he wants and it has the products he wants. When he adds all the reactions together, it has the correct stoichiometric amounts, and from there he can calculate what the expected enthalpy change, what the expected heat of reaction should be for that specific reaction. This is a lot like altitude, and we're going to start this screencast by looking at that as an example. So again, the whole reason why we can use this thing called Hess's law is because enthalpy is a state function, meaning that only the final and the initial states matter. So let's look at this example with altitude. Let's say that you're driving from Portland to Denver, and you've been told that the difference in altitude is 5,230 feet between Portland and Denver. But this is something that you want to confirm yourself. Well, on your trip, you stop twice, so you decide that those two spots are going to be good places to record the altitude and then calculate the difference from there. You stop once in Boise and once in Salt Lake City. As you go from Portland to Boise, you discover that the change in altitude is 2,680 feet. You spend the night in Boise, and then after that you go on to Salt Lake. After Salt Lake, you discover that the difference in altitude between Boise and Salt Lake is 1,496 feet. And then you go from Salt Lake to Denver, finishing up your trip, and the difference in altitude between those two cities is 1,054 feet. You want to figure out if your overall change in altitude is this 5,230 feet that you were told at the beginning. Well, because altitude is a state function, it means it only matters what the initial and final states are, in this case Portland and Denver. So essentially what we have here is we kind of have, in a way, 3 reactions, going from Portland to Boise, Boise to Salt Lake, and Salt Lake to Denver. Well, anything that shows up on one side of an equation, we cancel out on the other, leaving us with our initial and our final state, Portland and Denver. In order to calculate the overall altitude change, what you do is add up the altitudes that you are given. In this case, we know that Portland to Boise is 2,680, Boise to Salt Lake is 1,496, and Salt Lake to Denver is 1,054. And when you do, you discover that your overall altitude change is 5,230 feet. Thus proving that yes, altitude is a state function, and only the initial and the final states matter overall. So here is the technical definition then for Hess's law. For a given reaction, the enthalpy of that reaction can be found by summing the individual steps of a series of reactions that creates this overall reaction. So that sounds like a lot of words. Again, let's look at it with this example. So here we have methane gas reacting with oxygen gas to produce carbon dioxide and liquid water. Now, what we're saying is that we don't know what the enthalpy for this reaction is, and we want a way to be able to calculate it. Well, we can do so by looking up individual steps that will add up to create this overall reaction that we're looking at. Well, let's suppose then that these were the two thermochemical reactions that were at our disposal. We had methane gas reacting with oxygen gas to produce carbon dioxide and gaseous water, so water vapor. And when this reaction occurred, it released 802 kilojoules of energy. And then we had liquid water that would create gaseous water, and that would require 44 kilojoules of energy. Well, we can use these two steps, we can manipulate these so that they add up to the overall reaction that we're looking for, this one at the top up here. And we can then calculate this missing enthalpy of reaction because of that. When doing these problems with Hess's law, it often helps a lot to rewrite the reactions so that they are manipulated in your favor. We always want it to be that the products and the reactants are accurate. So that's the first thing that you should check. Now, looking at this, we can pretty clearly see that we want to have liquid water as a product. And currently, the only place where it is in these two reactions is as a reactant. So that tells us one step that we need to do. We need to flip the second reaction. So now we flipped it. We've now got that gaseous water is becoming liquid water. And you'll also notice that there was one other thing that I did. I had to make this enthalpy negative. And this is always going to be true. Whenever you flip a reaction, its enthalpy changes just the opposite. So this reaction is exothermic and will give off 44 kilojoules of heat. Looking at this, you might think that this is great. Now we can just add these up and we will have our reactants and products that we want. And that's slightly right, but if you also notice this, and this is going to be very key, which is that in the products, we need to have 2 moles of H2O. Currently, we only have 1 mole of H2O. In addition, we have that there are 2 moles of H2O in one of our steps, and we're only cancelling out one of them. So, we need to do one more thing, and that is that we need to multiply the bottom reaction by 2. Having done that, we now see that the enthalpy change of this reaction will give off 88 kilojoules of heat instead. And we're at a point now where we can add these two reactions together. And when we add them together, what we'll find is that the 2 moles of H2O gas will cancel each other out. And we'll be left with the exact reactants and products that we want. We want to have methane. We want to have 2 moles of oxygen. We want to have carbon dioxide and 1 mole of it. And then we also want to have 2 moles of liquid water. So our reactants and products are now good. In order to determine this enthalpy of the reaction overall that we're looking for, we simply add the 2 enthalpies that we had in each step. So the first step was negative 802 kilojoules. We add to that negative 88 kilojoules. We're going to get an answer of negative 890 kilojoules. This is a reaction that actually has been done, that actually is recorded, and this is in fact the heat of reaction that is given off when this reaction takes place. So in conclusion, this is Hess's law. This is a really useful tool for scientists to be able to use for particularly difficult reactions to conduct, to estimate how much heat will be given off or required for it to start. And it can only happen because enthalpy is a state function. Hopefully this is something that makes sense for you. If not, feel free to ask questions the next time that I see you. Thanks for listening.